Welcome to this explainer. Today, we're diving straight into the hidden rules of light. And look, we're not going to sit here staring at dense equations in some sterile lab. We're breaking down exactly how light interacts with the world in 3 dimensions. If you've ever paid attention to how high-end 3D visual video renders realistic environments, you know it all comes down to mimicking these exact physical laws. We're going to make the invisible completely visible for you right now. Let's get into it.
Okay, to ground us in reality, think about this. Why does a stick appear to bend when you poke it into a clear pond of water? You've seen this, right? You dip a perfectly straight stick into a lake, and bam, right at the surface, it looks like it snaps at an angle. It's kind of like a glitch in the Matrix. Your brain knows for a fact the stick is straight, but your eyes are feeding you a totally different, warped reality.
But here's the thing. Rainbows, mirages on a scorching highway, that bent stick, none of it is magic. It's just the predictable interaction of light waves, following strict, foundational rules when crossing between different materials. We call these invisible boundaries interfaces. When light hits the interface between, say, air and water, it has to make a split-second choice, reflect or refract. Understanding exactly why it makes that choice, that's what unlocks the whole shebang.
Section 1. The Path of Least Time.
So to really get this, we've got to travel back to the 17th century and meet Pierre Fermat, a brilliant French mathematician. Look at his original principle here. The actual path between 2 points taken by a beam of light is the one which is traversed in the least time. Think about how wild that is. Fermat basically personified light. He gave it a strategy. Light is literally the ultimate efficiency expert. It doesn't necessarily care about the shortest physical distance, like a straight line. It actively hunts for the route that burns the absolute least amount of time. It's a subtle distinction, but it completely dictates how light bends.
To wrap our heads around Fermat's idea, we need to talk about optical path length, or OPL. Basically, OPL is the geometric length multiplied by the medium's refractive index. What this means is that light's efficiency isn't just about physical distance. It's totally dependent on the density of the stuff it's traveling through. A physical inch through a vacuum, not the same as a physical inch through thick glass. The glass forces the light to work way harder and move slower, which massively bumps up that optical path length.
Take a look at these numbers. Different materials have different densities, which we represent with the index of refraction, or n. In a perfect vacuum, n is exactly 1.00. Light is absolutely flying at max speed. But as the material gets denser, that index number climbs and the light hits the brakes. Water is roughly 1.33, glass is about 1.50, and check out diamond down there at 2.4. A diamond slows light down tremendously. So, if a light beam wants to get from point A to point B in the absolute least amount of time, it's going to bend its physical path to stay in the faster medium, like air, as long as possible, minimizing its time in the slower medium. And boom, that is exactly why your stick looks bent.
Section 2. Huygens and the Wave.
Okay, so we know light tries to save time, but let's zoom in on the physical mechanics of how light actually travels through 3D space to pull this off. Enter Huygens' principle. Huygens proposed that every single point on a wavefront acts as a brand new source. These sources create spreading secondary wavelets that push outward. The new wavefront is just the envelope, the tangent line of all those expanding wavelets combined. Think of dropping a pebble in a pond, where every single ripple generates microscopic new ripples of its own. It's a beautiful, elegant way to visualize how waves spread and bend.
I like to call this the muddy highway effect. Imagine you're driving your car down a smooth paved highway and you approach a thick patch of mud at an angle. The tire that hits the mud first instantly loses speed, right? But the other tire is still spinning fast on the pavement. So what happens? The whole car tilts and swerves into the mud. Light literally does the exact same thing. When a wave front hits thick glass at an angle, the lower portion experiences a differential delay. It slows down first, which physically tilts the entire emerging wavefront. That is the mechanical reality behind refraction.
Section 3. Crossing Invisible Boundaries.
Now we're shifting focus to that exact fraction of a second when a wavefront crashes into a new material, using the work of Augustin-Jean Fresnel. Fresnel took this whole thing to the next level by applying wave optics to boundary behavior. He figured out that light decomposes into S-polarized and P-polarized waves. Basically, light oscillating side to side versus up and down. His Fresnel equations predict precisely how much incoming light bounces off as a reflection and how much punches through as transmission. And the golden rule here?
The electric and magnetic fields absolutely must remain continuous and in sync across that boundary. No breaking allowed.
So, when that light bounces, you get two distinct types of reflection. On the left, we've got specular reflection. This is when light hits a microscopically smooth surface, like a mirror, and reflects in one single, totally predictable direction. Over on the right is diffuse reflection, where light scatters everywhere because the surface is rough. But here's the secret. The overarching law of reflection, where the angle of incidence equals the angle of reflection, is always happening. Even on a rough surface, every single tiny ray is obeying the law. The rough terrain just sends them all packing in completely different directions.
Depending on how that light reflects or refracts, it creates different types of images. Real images happen when actual light rays physically converge at a point in 3D space. You could hold up a piece of paper and project a real image right onto it, like at a movie theater. Virtual images, on the other hand, happen when light rays only appear to diverge from a point. When you look in your bathroom mirror, you're seeing a virtual image. The light rays are bouncing off the glass into your eyes, but your brain traces them backward, projecting a 3D visual video of sorts behind the wall, right where no actual light exists.
Section 4. The magic of rainbows and mirages.
Let's step away from the whiteboard for a second and see these rules out in the wild. Ever wonder how a primary rainbow actually forms? Just picture a perfect 3D sphere of water, a single raindrop. Step 1. Sunlight enters the front of the drop and refracts, bending and slowing down because water is denser than air. Step 2. That light cruises through the water, hits the back boundary, and reflects inward. Step 3. It travels back to the front and refracts one last time as it exits back into the air, speeding up again. That exact combo, 2 refractions and 1 internal reflection, spreads the light into its distinct colors and literally paints the sky.
And what about mirages on a hot summer road? That's just Huygens' principle in action across invisible layers of air. The hot asphalt heats the air right above it, lowering its density and refractive index, while the cooler air higher up stays denser. As light travels down from the sky, the lower part of the wavefront speeds up in that hot air, which progressively curves the entire wave back upward toward you. But because our brains stubbornly assume light always travels in perfectly straight lines, we perceive that curved light is coming from the ground, giving us that classic illusion of a reflective water puddle.
Section 5. Harnessing Light's Hidden Rules. Of course, humanity hasn't just observed these principles. We've engineered them to build the modern world. Inside an optical fiber, light enters a glass core. If it hits the boundary between the core and the outer cladding at a shallow enough angle, past what we call the critical angle, it undergoes total internal reflection. Because that cladding has a lower index of refraction, the light literally cannot escape. It reflects 100% of the light back into the core over and over again, trapping it and guiding it for thousands of miles with virtually zero data loss. So how does it feel knowing that the exact same 17th century laws explaining a bent stick in a pond are powering our global internet through optical fibers today? Fermat's principle of least time and Huygens spreading wavelets aren't just textbook theory. They are literally carrying this very explainer and all the immersive 3D visual video content you watch on the daily to your screen right now at the speed of light. The universe has rules, and when we actually take the time to understand them, the possibilities are entirely limitless. Thanks for joining me on this explainer, and remember to keep looking closely at the world around you.